of introducing Sinan Akciz, who is a structural geologist, and paleoseismologist who conducts field-oriented research to better understand how continents deform over a range of timescales from decades to tens of millions of years. In his research, he investigates the times and magnitudes of past earthquakes along faults that affect people, how earthquakes change the topography, and how strain is distributed across wide shear zones. He's passionate about his teaching and motivated to train the next generation of field-oriented earth scientists. More importantly, Dr. Akciz is committed to preparing his students to be hardworking, critical thinkers, and lifelong learners, regardless of their career aspirations. Please welcome Dr. Sinan Akciz.
Thank you very much. A few things. I was originally born in Turkey. I came to US in 1997 to pursue my PhD degree. And as a field geologist, my research topic was in the eastern part of the Himalayas. So I was trying to understand how those mountain ranges formed. And then in 1999, there was a large magnitude earthquake near my hometown, Istanbul, where my friends and family members got affected severely. And then that was when I decided to change fields a little bit. So after I finished my PhD, I started working on earthquakes. So that's the paleoseismology or the earthquake geology component of it. And I am very honored to be here making this presentation because that earthquake was the motivation for me to do this study. And the main reason was that the research I did in the Himalayas was very exciting. It's scientifically very challenging, but at the same time, right after the earthquake, I felt very detached from the reality. I was doing a romantic research in a way, but there it was my family, friends, and other people that I grew up with ended up getting affected severely. So I decided to change my research field in such a way that it would have a societal impact, both scientifically and also socially. So I really welcome the opportunity to give this presentation and tell you a few things about perhaps things that you already know about the San Andreas Fault. Maybe, hopefully, there will be lots of things that are new, and we will see where we'll take it from there. And the way I generally make my presentations, like my lectures, is I can see every single one of you. This is not a very dark room. At any one point, if I can see a hand, I'll be welcome to entertain your questions. We can make it as interactive as possible. This is not just solid science and you go away with it. We can make it as interactive as we want. So feel free to interfere as well, as long as I can see you. That should be fine. So we will talk a little bit about the San Andreas Fault and some of the research that I was a part of for the last decade or so, and some of the new things that we have found and some of the challenges that came with it. So with that, I would like to start out with a couple of things about the San Andreas Fault, but faults in general, in particular strike-slip faults. This is a term that you might have heard of. This is the case where the plates move sideways. So it generally doesn't create any topography. Things move sideways. And regarding the San Andreas Fault, this motion is right lateral motion. And the way it works is, it's kind of shown. So this is the view of the San Andreas Fault, this linear feature right through here. This is the major plate boundary dividing or separating the North American plate from the Pacific plate. The motion along this section of the fault is about 4 centimeters a year, so a little over 2 inches a year. But a cartoon view of this fault, if we take a look at the cross-section of it, it's shown in this diagram, where the surface, as it's getting deformed, it's actually all the action is dominantly happening at depth. In California, this happens at about 8 to 10 kilometers. And this is what these two kind of greenish blocks are showing. That's the part that is continuously moving a couple of inches a year, close to 4 centimeters a year. The surface, on the other hand, is uppermost 8 to 10 kilometers part of it. This is the section in California. We refer to it as the locked section of the fault. So what that means is that it only ruptures in between or during the earthquakes. But in the time periods in between these earthquakes, it simply deforms elastically. So I have a small lab, kind of a demo unit that I showed to my students as well. So if I wasn't able to bring the actual the lab device here, but let me show you a video of what this actually means. The yellow part that you're seeing in this video, once it starts, it's actually a foam, which is representing that uppermost 10 kilometers part of the fault. And the hand crank is moving the lower part. It's a wooden plate, and it's simply moving it right laterally. And as you can see, the upper part, before an earthquake, it simply deforms. We can recognize this, and then it snaps. So that snap is the earthquake part of it. So we can record how much the surface is deforming in between the earthquakes. That tells us mostly about how fast this lower part is moving. And then when it reaches a certain limit, it snaps, and that's when the earthquake happens. So so this is kind of a background part of it. This is how the faults form. The surface part is separate from the lower part, and it's actually the lower part that moves continuously, and the uppermost part snaps when it's ready. Now, the big question is, how do you define when it's ready? Well, that's what we're trying to figure out. What is that limit that causes the earthquake to happen? But before we get into that, I would perhaps also to take your attention a little bit. And you might have seen this video. This is an animation of the ground shaking we expect to see if a large, let's say a magnitude 7.8, 7.9 earthquake happens along the San Andreas Fault. The assumption is that it's going to start near the Salton Sea down south. It's going to go through Palm Springs and up north. The color coding is indicating the intensity of this earthquake we expect. As you can see, right along the fault, which is this line, right along the fault line is where we expect to have this most intense shaking. And as it goes away from it, it's going to lessen. And this is a very traditional view of it. But the power of this animation is going to show itself in just a couple of seconds. And that is that we have since, for the people who have been working mostly on the geophysics end of these earthquake studies, have realized that these waves can also go through valleys, buried basins, and they can basically channel themselves. So here's the Huntington Beach. Even though we're far away from the fault, it actually receives these waves. And the other thing we have learned is that the topography, the high mountains also trap these waves. So once the waves come in, they get trapped, they bounce. It's kind of like throwing a stone into your bathtub full of water. It's going to generate waves that's going to go to the edges, it will bounce back in, it's going to hit each other, they will bounce back out. So what this animation is showing is that this large earthquake not only is going to create severe shaking, it's also going to create severe shaking in places far away from the fault zone. LA Basin is expected to shake if this magnitude earthquake happens, and if the earthquake happens with a rupture that starts from the south and moves to the north. LA Basin is expected to shake for close to 3 minutes, upwards of 3 minutes. Now, I have moved to this country in 1997. I've been living in California since 2005. You probably have been living here much longer than I have and experienced a lot more earthquakes than I ever had. I have the luxury of doing this research without having experienced any large magnitude earthquakes. So this shaking is anything more than you have ever experienced. I'll show you some slides. The Northridge Earthquake.
The color of the city names, does that mean anything, or are we just looking at those lines?
No,
Or is it intensity?
So the intensity is the color coding. And,
In the name of the city? Or
the color of the name of the city has nothing to do with the intensity of the shaking. It was just added as a purple lettering to make it visible on this gray ground. So this is a part we have got really good at, seismologists got really good at in the past decade or so. And one of the biggest advantages, as the computer systems supercomputers are getting better and faster, there's a lot of data that goes into these animations. This was done quite a number of years ago. There are new generations of it, but the message is the same. The expected shaking is upwards of 3 minutes. In the LA Basin's area. So this is not what I'm going to be talking about, but this is why it is important to know the past history of the fault system. Now, there was a lot of geological data that went into this animation. We had to tell them roughly where we expect the rupture to happen, roughly what its magnitude is supposed to be. And so those are the things that I'm going to be telling you about in terms of paleoseismic research. So, going back to things that I am a lot more familiar with, here's a view of the San Andreas Fault. In red are the places where we had historical records of these earthquakes. The most recent one was near, so these are magnitudes 7.8. Anyway. The largest one in the northern section of the fault happens in 1906. In the southern part where we are mostly interested in, there was one in 1857, the Fort Tejon earthquake. In magnitude-wise, they were both 1906 and the 1857 earthquakes were fairly similar. And prior to that, there was an earthquake in 1812. Apparently, there were 2 earthquakes separated by a couple of months. But the very, very southern portion of the fault has not ruptured since about 1680. So that's the motivation why in that previous animation, we think that's the next big earthquake, if it were to occur, is going to be starting in this very southern part of it and produce an earthquake. Right now it is capable of producing an earthquake magnitude 7.8, or on the order of 7.8, 7.9. Now, most of the data that I'm going to be showing you is collected in a place within the Carrizo National Monument. You might have seen pictures of this, or in when I give this presentation at scientific meetings or different versions of it. Wallace Creek is the type locality where the investigations along strike slip faults have started. It's preserved perfectly. There are no houses around. It's a desert-like setting. Everything is as crystal clear as it can be. And in the springtime, this is how it looks. If they get the rain in the right time, the wildflower, a couple of years ago, it didn't go this intense, but I highly recommend you to follow the news and see if the spring rains happen at the right time, that desert-like setting gets covered with wildflowers. And there's very, very interesting geology associated with this area as well. Now, what do we know about the San Andreas Fault besides these historical earthquakes, 1906, 1857, and 1812 earthquakes? Well, up until about 2004, 2005, the belief, and this is a quote from one of the articles that was published in that year, which was telling what many of the people thought at the time. This was developed over multiple decades of research. And the results of that research and the conventional wisdom was that San Andreas Fault, especially this section that ruptured in 1857, ruptured only during infrequent earthquakes, meaning separated by 250 years to close to 400 years, and only ruptures during large magnitude earthquakes. In other words, you only expect to see magnitude 7.8s and 8s, but there was no record of any magnitude 6s, 6.5s. The idea was that this is a very mature fault. It's been active for about 5 million years. It's established itself. It's only going to rupture. And this was a very critical thinking because the last earthquake was in 1857, roughly 150 years ago. When we tell you that the recurrence interval is roughly 250, 400 years, you all feel a big relief, sit back and relax and worry about other things. Well, just like anything else, this was also based on limited data. That's the beauty part of the science. We can go back to these literature, find out what this data is based on, and see what we can improve it. So I'll walk you through some of those things. But before getting you into a panic mode, let me show you this diagram. All these black dots on this figure show the earthquakes recorded between 1994 and 2013. There's some faint purple lines there. If you can't see them, that's excellent. They weren't really supposed to be there. If you see them, that's okay too. But the idea with this is, if you take those purple lines out, it is nearly impossible for you to locate the San Andreas Fault. Now, this is a major plate boundary that moves 4 centimeters a year. It should be whopping. It should have earthquakes all the time. Magnitude 1s, magnitude 2s. Okay. In this period, and if we go back in time, the data part does not really change. So just to make things a little bit clear, here's where the San Andreas Fault is. Well, you can all see this red line. I'll put this back and forth. There are only some sections where you see some seismicity, but for most of it, you can barely pick up any earthquakes. If there was no topography, no extra lines drawn, you wouldn't really see the San Andreas Fault. Now, this is interesting, mainly because this goes along with that previous interpretation that we shouldn't be expecting any large magnitude earthquakes anytime soon. But our only data is from 1857. So we're curious to know what's the past history of it. Instrumental records started with by the San Francisco earthquake. So for time periods that are prior to the 1900s, there's no instrumental record. So if we have earthquakes repeating every 200 to 400 years, we have to determine this with other methods. And that's where the study of paleoseismology, my specialty, comes in. And I'll show you some slides on how this data is collected. Our data collection is a little bit more complicated. We try to make the best out of it. So this is a picture that you might have seen from the San Francisco earthquake, an offset fence. And these are the offsets that, if you can go to the field immediately after the earthquake, you can make a measurement, and you can determine the offset amounts, and you can plot it on a diagram and see if it matches with the magnitude of the earthquake that's from the instrumental record. So this is very useful in terms of the magnitude part of it. These are more like the pictures that you're familiar seeing. This is the parking lot structure from Cal State Northridge. This was a magnitude 6.7 earthquake. Lasted only 10 to 20 seconds. If you have felt it, I have talked to quite a number of people, it felt like eternity. Now, take these 10 to 20 seconds, compare it to the 3 minutes of shaking that I've just described possible. You might have seen this picture from the Kobe earthquake in Japan, magnitude 6.9. Shaking lasted only about 20 seconds. Take a look at the damage it has created. This is liquefaction, this related, and this is happening in Japan, one of the countries that is best prepared for these earthquakes. But these things can happen. Again, the shaking was only 20 seconds. And we're trying to get you prepared for shaking that will last about 3 minutes. If that magnitude 7.8, 7.9 earthquake happens. Now the magnitude difference is only 1, 6.9 to 7.9, but the energy difference is about 30 times. It follows a logarithmic scale. It's not just a simple linear relationship. Now, this is a recent earthquake that you might have heard of, the South Napa earthquake. This was only magnitude, it was on the order of 6, I think 6.2. And this is, in order to get you to the type of studies that I do, this slide is important because what happens during an earthquake, besides the structural damage in here? We see surface cracking. This is a very small earthquake, but it still created some minute offsets, it created cracking, and then in order to get going with our lives, we like to fill those gaps, right? The construction crews go in right away and fill those holes so that we can go on with our daily lives. Well, the Earth itself does a very similar thing, just at a much smaller pace. So these are some photographs taken after an earthquake of, this is a surface rupture. The picture is taken about 2 days after the earthquake. You can see the scarp. There's some motions following the earthquake. Just to remind you that the offsets or the earthquake itself is not the only thing that damages. Will have aftershocks or slip occurring even after the earthquake. So this scarp looks like it has got enhanced a little bit, but give it about 2 years after the earthquake, the surface will take care of itself and it will all smoothen itself out. Now, the smoothing is important because it covers that scar that was visible before. And those are the things that we'll look for in the research that I do, the field geology that we do. Now, there are a lot...
The recovery, it moves back, or is it just filled in?
This is just erosion. It just gets filled in. Once the slip happens, it is a permanent deformation. It stays there, but the scarp itself ends up getting subdued. This was, in this picture, this is in a soil, so easily erodible section. If it was bedrock, it probably would have stayed as a cliff face for a lot longer. Now, there are lots of other evidences that we can recognize regarding these earthquakes. So this is what this cartoon on the left side is showing. So these are some of the things that might happen during an earthquake. So I have some marker beds. These are cartoon drawings. The red line is indicating a fault. And then this blue unit is the first unit that caps that earthquake. So this is important for us to recognize in the field. But what are some of these evidences? We can see vertical offsets. We can see juxtaposition of completely different stratigraphy. If the slip is too much, we can see this. We can see the exact same units, just different thicknesses. This is a very typical occurrence if the earthquake is occurring along alluvial fans. We can create both a vertical offset and also a fissure opening, and that fissure might end up getting filled up over time. This is what I showed you in that photograph earlier. We can cause tilting, and once the tilting occurs, there is erosion. It tries to plane things off, and then the next set of layers will come and deposit horizontally. Or we can have a scarp development like the previous picture. It's going to fill that space with a colluvium, so it will kind of smoothen it out, and then all the other layers will fill that gap, and then finally create these horizontal layers. Now, so on the left is the idealistic view of what earthquakes should be doing. On the right is an actual trench log, and I'll show you what the trench looks like in just a little bit, on what these earthquakes look like. So let me go through some of these with you. I don't expect to make you paleoseismologists at the end of these 2 seconds, but let's take a look at some of these evidences. This B perhaps is going to be one of the easiest ones to see. As you can see, it's going through these blue, red, and light blue layers, and then it gets truncated here. So this top of this light blue layer was probably at the surface at the time of the earthquake. The earthquake creates this fissure, and then it ends up getting filled with these different green shades of units. At a later time, or at the same time, take a look at this. This blue unit has been kind of upwards thrown. So we call that a mole track. It kind of looks like a fissure, but there was some motion sideways and also a little bit of a compression. So it's kind of like a sidewalk during construction. You can see a lot of it on campus right now. As the backhoe kind of moves the concrete, it kind of piles up a little bit and it creates this mole track. So this surface deformation gets capped with these green units. So this is all evidence of an earthquake. There's no other depositional mechanism that can create this kind of a disruption. So when we know that we're on the fault zone and we see these evidences, we mark this as an earthquake evidence. But as you can see, these faults reach only to this light blue layer. There are additional faults that go up to higher levels. So we can go through these stratigraphic relationships or cross-cutting relationships to recognize multiple different earthquakes. So here's another evidence. This is a figure from one of our publications. I'll walk you through with some of these events and highlighting this kind of pebbly unit with these, each one of the pebbles have been circled with a scale. The red line indicates the fault, it creates some disruption, and the purple line indicates a layer that wasn't affected by that fault. At a later time,
If these are deep in the earth, how do they know this structure?
this is only about 5 feet below the surface. These are all surface. I'll show you a picture to put it into a context. Here's another fault with red lines going through these purple unit, and then it gets capped. All the layers above that purple line, which is labeled as event C, they haven't been affected by that earthquake. New layers form. So the more recent earthquake, so we assume these faults are reaching to the surface. There's a whole other complication if the fault doesn't reach surface. But our scale of observation is we are 5 to 10 feet deep at most. So if it's anything coming up within a couple of feet, so we know that these are surface rupturing earthquakes. As paleoseismologists, this is another question that we end up getting asked. This type of surface deformation will only occur with earthquakes that have a magnitude 6 or higher. I think the smallest magnitude earthquake that had a surface deformation cracking was about magnitude 5.5 recorded in one place. So when I get these automated messages from USGS, my phone is set up to magnitude 6.5 and higher, because that's when the surface deformation occurs. That's when my specialty kicks in. In all the other earthquakes, I'm not particularly useful. So this is the fun part of my work. How do those detailed logs where we determine these earthquake information are obtained? Well, it's we have to hire, we cannot do this by hand. We have to hire excavators or backhoes. So we go to places where we know exactly where the fault is located. And we open these trenches that are perpendicular to it to see this evidence of past cracking and filling. These trenches are, for the most part in California, they're about 12 feet deep. 11 feet deep, that's pretty much the limits we can do with OSHA standards. We can go down to 17 feet if we use this bench style. So we can go down about 5 feet and another 11 feet down. There are special places where we can do, this is a style where we're creating these vertical walls. And we put these shores inside so that the walls don't collapse. And this type of research generally takes about a month or so. You need to have a crew of about 6 to 10 people. The trenches are about 3 feet wide. The excavator generally opens 4 feet, but they're mostly about 3 feet wide. The length of it is about the length of this room, actually much larger, about maybe a diagonal, about 90 feet long. That's a typical trench length. The fault zone itself is about 20 feet wide, but the trenches are opened long enough just so that we don't miss any of the earthquake evidences. Even though it looks like a sharp line on the surface, it almost never is a straight line. And then a big effort of cleaning starts. So this is kind of a ridiculous effort to lots of people when I show this because we're in the middle of a desert. Everything is soil, everything is dusty and sand. And there we are with leaf blowers kind of cleaning the walls. This is important because when the backhoe opens it, take a look at all these scour marks. You can hardly see anything on in these trenches. But after about a day or two's effort of cleaning, the same wall looks, the stratigraphy appears, and this is where we spent our time trying to determine those earthquake evidences. Most of the work goes into logging, so we take pictures. Those pictures get mosaiced together, we print them, and then we work on 1 to 10 scale. In other words, every 10 centimeters on these walls, or let's say about, what would that be, about 5 inches. It will be about half an inch. So 1 to 10 scale, and every pebble, large pebble, that's bigger than about this size, a couple of inches, it has to be drawn to scale on that map. Because when these earthquakes happen, the offsets, sometimes it's on the order of only about a couple of inches. In order to recognize it, we have to map it in detail. A regular geological map that USGS does, that's the type of map we show for our teaching purposes, it's drawn at 1 to 5,000, sometimes 1 to 25,000 scale. This is 1 to 10. So every single screw, if we were to do that, every single screw on these chairs would have been mapped in detail. So most of it, this is the labor-intensive part. The other reason is you want to do a good job with it. You spend all this effort and energy opening these trenches. Within a month, they get closed, and almost they're permanently closed. That's the time you have to collect this data until the next year arrives. So what do some of these evidences look like? To many of you, this is just going to look like a grayish, brownish layers. There's hardly anything to see. It blends in. I'll mark some of the layers that we see after spending some time. Here's one of, I'll go back and forth, perhaps. There's a dark layer right where these cayenne lines are. Here's another offset layer, and here's another layer. As you can see, the red nails are put in places where we cannot continue any of these contacts. And it's also showing this vertical displacement. So not only there's a gap, there's also a vertical displacement. That's one of our evidences for how we recognize the earthquakes. The red line is where the fault was. It goes beyond the picture. And there's another one here on this side as well. So these are the types of evidences that we look for. Now, within a 15 feet wide zone, 2 faces of the trench, this takes a while to fully document it. It also takes multiple trenches. Most of this research gets done over multiple years. Again, we can open about 2 trenches every summer with a crew of about 10, multiple students, 1 or 2 faculty, but the data needs to be replicated. So in a physics lab or a chemistry lab, you can replicate an experiment at the comfort of your lab. We replicate it by opening new trenches. So all of this research takes a couple of years. It's never a one-time event. This picture is showing a place where I have done most of my research, where this place is called the Bidart Fan. It's a private property within the Carrizo National Monument, and the landowner has been gracious in letting us do all this excavation. BLM land is not known to be very friendly in permitting this type of research, though we have been extremely lucky with the type of work we did with them. Now, the other thing that you'll recognize in this area is that you can see the San Andreas Fault scar right through here. It's kind of like a knife cut, right? It comes up through here, and then by the time you come here, it becomes a little bit blurry, but at the same time, you also lose all the topography. Now, this is important because it means this is an alluvial fan. So whenever there's a rainstorm or enough water that brings all these sediments from the nearby hills called the temblors, very appropriately named with all the earthquakes they have in the area, and then those sediments come and cover these earthquake evidences, these surface structure evidences. So in a way, those are the places we go and do our trenching because we want these scarps, we want these fissures to be preserved. So we need to go to places where there's sedimentation. Now, that's also tricky. We don't want too much sedimentation because then it's going to get buried too deep. We want it just the right amount so that within our limits of 10 to 17 feet, let's say, we see as many earthquake evidences as possible. If we have 4 feet of deposits after each earthquake, we go down about 10 feet and we would be seeing only 2 earthquakes, if we're lucky.
What causes the difference? Some earthquakes go this way, they're shifting, and others are undulating. That's how we feel it. What causes the difference?
So it is in the plate tectonic setting. Plates move in 3 different ways. So think of it as a ball, and the skin of the ball is broken down into pieces. So those pieces can either move apart, where we will form the oceans, or they get close to one another, and that's when you'll see that crumbling and the mountains. But if the volume of that ball is not changing, there needs to be another fault that connects these two, and that's the strike-slip faults. So that's when they go sideways. Now the San Andreas Fault in this location, there's a subduction zone, so there's compression to the north, there's extension to the south, and the San Andreas Fault is just a sideways motion. So that's a large-scale motion of the plates. So it's not local. It is what the plate tectonics is determining. So if we just go up north, past San Francisco, like towards Oregon, all the structures that you'll see associated with these faults, they will all be compressional. They'll all be crumbling up. But along the San Andreas, it's sideways. Okay. We also, when we do our research, we have an unofficial term for an event. We call it a trench party. Now, this is our insight review. The reason, and we call the people that I'm trying to describe these earthquake evidences, we call them the trench police. So once we make our line drawings and get them published or send them for a review, so they're all nice, colorful figures, but this is one type of work where you can't really replicate in a different lab setting. So we invite geologists, paleoseismologists from USGS, California Geological Survey, and other academicians to take a look at these earthquake evidences on site. There's big discussions that go on. You get up close. They drill you with all of the evidences that describe. So these generally take about half a day to a full day, depending on the shade, depending on the number of earthquake evidences you have. But there's detailed discussions that go on right at the site. And then we produce these nice, colorful diagrams. Again, I can show you these diagrams. Maybe some will make sense, maybe some will not make any sense. However, these are kind of finished products. There's always some interpretation associated with them, where we're representing a detailed field observation into a figure that everybody can understand. But where I end every single one of these red lines with respect to these stratigraphic units is very critical, because that we're going to be using those to identify different earthquakes of different ages. And in the middle of nowhere, perhaps this is not too critical, but when you're talking about the number of earthquakes and recurrence intervals in California, this is very critical. So there's extra effort that goes into this type of research. So here's another trench log. This kind of shaded area is the zoomed up, blown up version of it. Let me show a couple of places where you might be able to recognize these earthquakes. Let's take a look at this fault. It comes and offsets all of these green, up to the green layer. And then it gets covered with these purple units. So this is one place. But here's the red line that I'm talking about. Goes up, affects all those green layers. and then it gets capped by those purple. And if you move a little bit to the right, in here, the purple layers ends up getting affected. So in here, and a combination of about 2 trenches, 4 walls, we see that there's evidence for 6 surface rupture earthquakes along this section of the San Andreas Fault. Now, recognizing the earthquakes is one thing. It makes us extremely excited because there are lots of trenches where we don't see these earthquake evidences. There's either too much erosion, not enough deposition, or all of these earthquakes are right on top of each other, so we can't distinguish them apart. But after we have these earthquakes, our task is not done, because the big question that we need to ask is, well, when did these earthquakes happen? There are lots of places where the earthquake record is preserved, however, there's no datable material. So one of the kind of special things about this particular location is that it is also full of charcoal that is coming from these Temblor ranges. And that alluvial setting I have mentioned, with each rainstorm, it's bringing the sediments. And imagine natural forest fires happening, and after that, a rainstorm brings all that charcoal, and it buries these earthquake evidences. So that's another reason why we open multiple trenches. We take a look at these, we try to replicate these earthquake evidences and also increase our chances of finding these charcoal pieces. The way we work with the dating part is we can never give you an exact date on what the prehistoric earthquake has occurred. We can only give you a range. And the way it works is, for example, for an earthquake, let's take a look at this earthquake. We take a look at the charcoal samples that have been affected. Oh, thank you. So here's one earthquake. We take these black numbers are very idealistic cases of the ages of the charcoal samples we have collected. So we try to collect samples as close as possible to the surface during which the earthquake happened, and also layers that immediately or very close to immediately capping that earthquake. So in this case, we can say that the event 2 or earthquake 2 has happened sometime between 1100 and 1150. Now this is a super ideal case. Let's take a look at this one. Here we didn't get all that lucky, it gets affected all the way here, but we have a charcoal sample from a much lower unit. So the best we can say is that this most recent earthquake happened at about 1200 years, but before 1350. So then this is going to have a much larger uncertainty associated with it. 1200, and there's a 1300. So this earthquake actually happened between 1300 and 1350. There's the outside. Now, okay. So this was the previous example was how we determine the ages of the earthquakes in the most simplistic way. When we submit this data to a publication, this is what the data looks like. This is the oldest layers going up, and as you can see, the ages are getting younger and younger. From this, we can, the computer or the models we have can do a probabilistic analysis of what the ages of these earthquakes will be. I don't expect you to read those numbers because I'll show you the summary in just a little bit. But again, this is one of the places along the San Andreas Fault where we've been really lucky to collect all of these charcoal samples. Now, here's the punchline. Once we look at the ages of these earthquakes, we have, as I have said, we have recognized 6 earthquakes. We know the most recent one was in 1857. These different color-coded, these ones are just the mean ages of the spread of ages we have. Remember I said we can only constrain, we can bracket it, we can never give a direct age of it. These are the ranges of those earthquakes, and I just picked the mean of it, and I'm reporting those numbers just to get a conversation going. So if we look at these, we have seen that our 6 most recent earthquake, this event F, has occurred sometime within the 1400s. If I include the errors or the uncertainties on it, it's from about 1390 or so. So between about 1400s and 1857, we had 6 earthquakes. So if we look at the recurrence interval, so the time in between these earthquakes, if we make that calculation, it's about 90 years, 90 plus or minus 40 years. Now this is a number which is very different from what I started out with, which was 250 years to 400 years. Now this average, if we go into the details a little bit, is also showing us that some of these earthquakes are separated by only about 40 years. Some are separated by about 150 years, close to 150 years. So it hasn't been very systematic either. The time interval between the earthquakes have also varied. So this brings up all kinds of interesting questions, because the assumption, again with that second or third slide that I showed you, was that we have infrequent and only large magnitude earthquakes. Well, we know 1857 was large. Do we think every single one of these past ones were also magnitude 7.8, 7.9? That's one assumption, but it is hard to produce that large magnitude earthquakes with about 50-year intervals. Perhaps smaller ones, but not as large. So that's where these, once we have the ages, that's where the next set of questions ended up starting. I said, well, how big were these earthquakes? This is important because if we end up showing that the earthquake magnitudes in the past varied, and the time interval between the earthquakes have varied, more than 150 years have passed, we should perhaps be a little bit more prepared than what we thought we should be expecting about 10 years ago. Now, there are a couple of ways we can determine the magnitude of past earthquakes. So this plot on the right is showing like empirical data. So people have gone out to the field immediately after an earthquake. They measured the length of this surface rupture, the length of the surface crack. And so there's a rough linear relationship which indicates that the larger the magnitude of the earthquake, the longer the surface rupture is going to be. So a 10-kilometer surface rupture is going to be about the magnitude 5.2, 5.3. A 100-kilometer rupture is going to be about magnitude 6. Okay. Paleoseismologically, we cannot go and map these surface ruptures that occurred in the past. So what do? We do this trenching work I have just described to you on places where we can get a permit. That's the biggest limitation. Wherever we can get a permit, if the sedimentation is right, those are some of the locations where we have collected this data. So from this, we determine the ages of the earthquakes, and that is what each one of these lines are. So on the y-axis, I have the calendar years. This is 2000 close to present. This is going back in time. The length of the colored line indicates the uncertainty we have for those individual earthquakes. These are multiple locations where this data has been collected, and they're color-coded. The red lines I have drawn here are one of many options of correlating earthquakes in between these sites. This is exactly, it's not a lot different than what my 7-year-old son does if I give him 2 dots and ask him to connect the dots. It's not any different than that. So we can come up with multiple different interpretations in this one. It's not unique, unfortunately. In this particular case, the attempt was to make each one of these earthquakes as big as possible. So, for example, 1857, we know its rupture length. It went all the way through here. So this was about a 300-kilometer rupture. This is a possibility for the penultimate earthquake, or the earthquake just prior to it. But in this record, with our best attempts, there's only 2 lines that are as long as the 1857 rupture. In other words, probably only one that was in the early 1500s. It's possible that it was also 1857-like. But all the others were smaller. These are not small magnitude earthquakes. It's 200 kilometers. We're still in the sevens. Don't get me wrong. It's just they're magnitude-wise slightly smaller earthquakes. Now the other thing we can do is, and this is the second part of the plot, is that we also know that there is a relationship, again, a roughly linear relationship between the magnitude of the earthquake and the amount of offset. I showed you a picture of Napa earlier on. I can show that, and I'll show you that in just a little bit. But here's what this says. A surface rupture, so let's say a surface rupture of about 10 kilometers roughly coincides with a magnitude 6. That should also, on average, have about a 20 centimeter displacement. A 100-kilometer rupture, which is about a magnitude close to 7, okay, that should create about a 1 meter slip, which is right here. So if we can determine the slip from these past earthquakes, we might have an idea on what their magnitudes were. And we can correct it with the rupture lengths we have determined or speculated from the previous figure. So, just to put things into a perspective, here's the Napa earthquake, magnitude 6, 2014. The displacements are on the order of about a couple of inches. Here's the El Mayor earthquake. I did extensive field work after the earthquake in 2011. This is a fault scarp. The measuring tape is roughly the orientation of how slip has occurred. That's close to, it's over 4 meters of slip that occurred during that magnitude 7.2 earthquake. Now, are you ready for this next one? This is a fault in New Zealand. This fault, there's a channel. Here's a modern channel that comes in here. Now, in the previous earthquake, this channel used to be right here. It has displaced nearly 18 meters during one earthquake in 1855. So let me demonstrate this. 15 meters. Sometimes the pictures are misleading. Say that I was sitting right here and the fault is right between us. I'm out the door. I still have one more step. Actually, that was 15. I have 4 more steps. That's what happened in the previous earthquake, 15 meters. These are large. So this is what the magnitude 8.2, I believe, can do. So these are large magnitude earthquakes. So what happened was with that displacement, that channel got completely displaced. It formed a new one, and then that got displaced. So there's records of 2 past earthquakes in here. There's no other record of an earthquake, so we know that at least the last one produced 18 meters of slip. Now, luckily, we don't expect that large of a slip here in California, but it's nearly 10 meters. That's what we expect. Okay, so one of the things that we have done. How much time do I have? I will. About 7 minutes. 27 minutes. Excellent. One of the things that happened as we were doing our earthquake dating project was that starting in 2004, a very detailed topographic data set was started to be collected. This is LiDAR, so it's you can fly this instrument with a helicopter or an airplane. It shoots laser beams, thousands of them in a second. Those laser beams come down, hit the surface, it gets received by the airplane. And then depending on how slow and how low you fly, you can get very, very high resolution topographic data sets. And that helps you recognize these offset features and make some measurements on their offset values as well. So, in other words, when this original work was done in the 1970s, this is all they had, aerial photographs and regular USGS topographic maps. These are the maps you would take when you go on a hike. Then there was satellite-based digital topography data. They said about 30 to 90 meter resolution. So this is covering the exact same area. You can pick up features with the hill shading. You can pick up the features a little bit better. But take a look at what this laser drive data shows. It shows a lot more details. So it enables us to recognize much more subtle features. So that's the punchline. But a bigger reality of it is that this data is digital. You can open these up in front of your computer. You don't have to go in the middle of the desert. You can open it at the comfort of your office, take a look at this data and go to the field to confirm or deny. But you can do a lot of work just in the office. Now this is what the San Andreas Fault looks like. It's just a different perspective, still covering the exact same area. So this is what we have done. We have gone and identified channels, because they're very valuable piercing lines. In other words, they used to be a linear feature prior to an earthquake. An earthquake happens, it offsets them. And if they get abandoned, that is a unique value on what the displacement was during that earthquake. Now, these are kind of, they look like blurry images, but I'll walk you through them. These are 4 different channels. The blue lines, hopefully they are going to be visible. The blue lines are where we have recognized these channels. And if you look at them, what separates them is going to be the fault. We'll add the faults, and then what we can do, again, at the comfort of your computer screen, you can restore them to what their original geometry should be. Okay? So the trick is to recognize them. You put your reference lines, you restore them, and you measure the amount of displacement. So one of the things we ended up finding was that despite the initial observations of close to 10 meters of slip in this area where I provided the earthquake ages, there are upwards of 30 offset measurements that were made that were only about 5.5 meters. So much smaller displacement amounts. Now it turns out that this doesn't really affect the magnitude of the earthquake, because it was only a small portion of it. But it says that in 1857, this large earthquake produced about 5.5 meters of displacement. Now this is only the most recent earthquake. This color-coded graph, let me walk you through with it, is showing a plot of all the other observations that we have made. So on the x-axis, we have distance along a fault. So we looked at these offset channels along about 100 kilometers, let's say a 60-mile portion of it. And on the y-axis, we have recognized, this is the displacement amounts. So and the color coding is based on what we have recognized as possible contemporaneous offsets. So the smallest one is the easiest to interpret. This is the displacement that has occurred in 1857. Now prior to it, we see a peak at about 10 meters, and this is just a cumulative plot of it. See another peak at about 15 meters, 20, 25, and then some random numbers. But it looks like we see this easily recognizable kind of 5-ish peaks. Now this is not the color coding is not unique. If we go and do nitty-picky job, we can draw some other lines. But at a first glance, the data suggests that we're seeing these multiples of 5-meter displacements. Now here's the easiest interpretation of this data. We have a channel that goes across the fault. We have an earthquake. That earthquake creates a 5-meter displacement. A new channel forms at a different location. We have another earthquake. Now that first channel that got displaced 5 meters in the previous earthquake is now displaced 10 meters. The more recent one is offset only 5 meters. So that's why we can tell the most recent was 5, the one prior to it was also 5. Let's say we form another channel, we have another earthquake, now we'll have 5 meters, 10 meters, and 15 meters. And we can map this all along this 110 kilometer section of it. Now what's the biggest assumption that we make with this animation, small animation? we assume a channel, a set of channels form in between the earthquakes. Now, this might be reasonable if the earthquakes are 200, 400 years apart. But if they're only far apart by 40 years, 100 years, is that still a reasonable assumption? So that's one of the things we went ahead and started to test. It turns out that dating channels is not an easy task, and we're still struggling with it. But here's the motivation part of it. If we have earthquakes every 100 years along the San Andreas, and each time the earthquake occurred, they were 5-meter offsets. That fault has to be moving about 5 centimeters a year. Now, from the GPS, from all other geological data, we know that slip is only about 3.6 centimeters. So a little over 2 inches. We're not reaching the 5 centimeter level. So something else must be occurring. It's also, there's nowhere we have any record of producing that same magnitude, same slip with such variable recurrence intervals. So there is a much easier interpretation for that data, and that's our working hypothesis right now. If only we can date these channels, we'll be able to prove or disprove it. But let me walk you through our hypothesis. Our hypothesis is that channels do not form regularly, at least in this desert setting. So for new channels to form, probably the biggest the factor that forms these channels is going to be heavy precipitation events. And not just like a one major storm that lasts for a couple of days. This is probably several weeks long of major storms. And those don't happen all that frequent, because during those storms, the existing channels are more than capable of carrying the water down. So if channels do not occur in between these earthquakes, then what might happen, the evidence of multiple earthquakes might be hidden in these channels. So let me walk you through some assumptions. Let's say we have formed a channel in about 1418, and we have an earthquake in 1462. These dates are directly coming from our trenches. So that will produce about a 1.6 meter slip. We have another earthquake. We have no other channel forming. And then that channel will now be having a total offset of about 5.2 meters. At a different location, after 2 earthquakes, we form a new channel. We offset it during 1 earthquake. We offset it during 2 earthquakes. Now take a look at it. Our first channel, our oldest channel, is after 4 earthquakes, has produced about 10 meters of slip. Our second channel, after 2 earthquakes, has formed about 5 meters of slip. We form a new channel, and they all experience roughly a 5-meter slip afterwards. Now let's take a look at this data. This creates some 5-meter channels, 10-meter channels, and 15-meter channels. If we look at the plot of it, it's identical to the one that I have shown you. In other words, if the channels do not form very regularly, we can still produce that exact same distribution of channel offsets. So that's where our research is going right now, trying to test that assumption. Do these form in between the earthquakes, or do they experience multiple earthquakes? So with that, let me wrap up this has been kind of a talk that covered multiple different topics. Over the years, we only attack a single part of it and go into the detail. But hopefully, I was able to show you that this field geology data is showing us that this part of the San Andreas that last ruptured in 1857 has experienced 6 earthquakes since about 1400s, late 1300s. Those 6 earthquakes have an average recurrence interval of about 80 years or so. The last earthquake produced about 5.5 meters of slip. And at least in this time period, there was never a time when slip occurred more than 5.5 meters. So you don't have to worry about getting displaced all the way across the room, maybe only up until Janus from the side. Okay, that's still a little scary, but at least not as drastic as the other one. Okay. So what that means is that the slip must have varied. Now this is a very different view than what I started you out with, perhaps with what you thought about the San Andreas, with large, infrequent earthquakes. What the data is suggesting is variable recurrence intervals, anywhere from about 50-ish years to 150 years. Variable slip, anywhere from sub-meters to no more than about 6, at least in this time period. And if you combine the two, it means it also is capable of producing different magnitudes of earthquakes. So we don't need to just get prepared for a magnitude 7.9. Even a magnitude 6, magnitude 7, which don't look as scary compared to a 7.9, is entirely possible. Here's the scary part. For the past 150 years or so, if you multiply that time with the slip that occurs at depth, like that model I showed you, at about 3.6 centimeters a year, at depth, it has already moved about 5 meters. Now we're coming to that magic number. It has moved as much as it had slipped during the 1857 earthquake. Now it doesn't say that that's what's going to happen with the next earthquake, but we can say for sure that enough time has passed to produce an earthquake that is just like the 1857. Yes?
What I understand in that area, there was a landslide and a flood that was caused by the quake. But now that's pretty close to where Pyramid Lake is now, up there, all the water thing. So if we had that kind of a quake now, would that displace the lake a little bit?
Probably, but I have to look at the map. I cannot give an answer on top of my head right now. But like the shaking, the offsets is one of the things that we're most worried about. But what you're saying is, what generally follows these earthquakes is going to be landslides and liquefaction. And that's going to, and I can't imagine what kind of an extra disruption that's going to be.
We used to go hiking in that area. Now it's all underwater.
And they're steep. They're steep faces. Yes?
If I heard you right, you're basically stating that it's been over 150 years since we've had a major San Andreas Fault earthquake, but that it's been 350 years for the lower part of the San Andreas Fault, closer to us. Listening to the lecture makes me want to run home and sell my house, rent something. Are we doing any better with predicting earthquakes?
No. There's, the effort has moved away from predicting to, at best, trying to forecast. And so let's get that part kind of cleared. There's not a systematic research that goes into it right now, just because of many decades of failed attempts. Yes?
You're speaking only of San Andreas, but a few folks here, they experienced Rupture, and I had just moved here, and the ground moves, and it's 1,000 locomotives. We got a lot of baby faults hanging around, and so you're talking San Andreas, the mama, but we got all these other faults that can cause very considerable damage. And just 2 or 3 years ago, in just La Habra, a little old 3, 5, or 4, if you were sitting on top of it, which we were half a block, we had like $30,000 of damage. So this is just the one guy, and now how do you guys like a lot of work to research the others?
So we haven't really connected before this talk, but I have a slide just for that. I was expecting a local connection. So this is the Whittier Fault in orange. This is a place, so this is my 3rd year at Cal State Fullerton. This is a fault system that I would very much like to study and learn more about because of the proximity. And maybe this is something you can help me out, because
Had a big fault there in the 87 Whittier. Well, that was
So here's what we know about this fault system. A part of it is unpublished. We actually don't know too much about it. So what we know at best, and this is the published part, it moves about 3 millimeters a year. Now, this is 1/10. It's hardly anything compared to the San Andreas Fault. But of all the faults that I can show on a fault map of California, within LA Basin, if this data is true, it's the fastest moving fault within LA Basin. Fastest. Everything else is a millimeter, sub-millimeter. We hardly know anything about the ages of the past earthquakes on it. There's unpublished data that says the most recent earthquakes was sometime in the 1400s, sometime between 1400 to 2000 or 2200 BP. So about 0 AD, let's say. And the one prior to it, 3000 or about 30, let's say about 3000 years BP. This is unpublished and based on very limited data. So, Whittier Fault, we know it can shake. It moves, one of the scariest faults. We don't know anything about the ages of the earthquakes that ruptured it. Going back to one of my, I said this multiple times, the biggest issue we have the techniques. We know where to look for, where to get this data. The biggest issue is getting the permit from the landowners to help us open the trenches. So, if you know of anybody who has a property along the Whittier Fault, have connections, I will leave my, well, Janice can give my contact information. I would love to get in touch with you to figure out how we can open those trenches and get the ages. There's no other instrumental data that's going to tell us that. Yes?
My understanding, there's about 5 major land routes into the Southern California. What's the chances of those being disrupted in a larger... I-10 in particular, I left that slide. For that shakeout scenario, which starts in the southern part, it's not just I-10 gets completely damaged, but not only I-10, the railroads, fiber optic cable, oil line, or the power lines, oil line, natural gas lines, and water. They are all expected to get damaged. Now that animation that I have shown you, it's nearly 10 years old. So I have to give credit to the state, LA County, all the public workers. They have been doing a tremendous job in terms of getting prepared for it. So at least now everybody accepts that this might happen. And when it happens, there's nothing we can do about it. When it happens, what is it that we need to do for a quick recovery? Because that's what they have learned from Katrina. They said, we have to bring in the water, we have to bring in the power so people stay. If not, they will all leave. So there's mechanisms in place for a speedier recovery than it was ever thought about a decade ago. So we're in better hands, and they're still working on it. Yeah. So the second one is easier to answer. There's no earthquake weather. And for the past decade or so, almost nobody talks about it. So I'll leave it at that one. There's earthquakes happen. Some of you have already mentioned tens, thousands of them if you talk about it globally. When it's sunny here, it's rainy back home in Turkey. It's tropical in some other places. Earthquakes happen in all types of weather conditions. The first one, regarding the first one, what causes these earthquakes is the motion of these plates. That first slide I have shown you, under what borders these moving plates is in constant motion. So strike-slip faults at depth, like 10, 15 kilometers of depth, about 10 miles, let's say, they are constantly moving. It's only the surface that ends up rupturing in these kind of breaks, but it's in constant motion. And that is regarding, we have the oceans pushing the plates apart. Once they subduct, they actually pull
There's the mantle convection, which is heat-driven, that drags the plates. So there are lots of other forces that causes these plates to move. And that's what causes the earthquake. The earthquakes, again, the deeper parts of it are in constant motion. It's only the surface that kind of sticks, and then it reaches a level and then breaks. But otherwise, it's in constant motion. Yes?
The part that's in constant motion, that's liquid rock, isn't it?
No, 10 kilometers of depth, it's still brittle. So at 10 kilometers, one of the things that happens is on average, the temperature reaches about 300 degrees centigrade. And that's when the quartz crystal starts to recrystallize, so they're no longer solid. So that rock ends up having some brittle parts, which breaks, and also some kind of very viscous parts that can flow. And also those are so that's when the continuous motions happen. And it forms beautiful rocks. If you ever go towards Borrego Springs, what is it, Montezuma Highway, perhaps? There are lots of pullouts. If you ever stop along one of the pullouts, you'll see these grayish rocks that have these kind of blobs of white crystals and black surrounding material. And those are coming from those 10, 15 kilometers of depth. So those are the places where we know how these faults look like at those depths.
I want to zoom the grade you're talking about.
It's
from 4,000 feet down to 700 feet.
Yes.
In 10 miles.
That's the one. Yes?
You said that other government agencies were not cooperative in letting you dig on their property. Why is that?
They all have their own reasons for it. Fish and Game Life, for example, their major aim is to protect the habitats there. So our trenching activity ends up becoming disruptive.
You're only there for a short period of time when you close it up, don't you?
We try to accommodate most of their needs. So BLM in Carrizo National Monument, I have to give them credit. When we are desperate, we do seek their help to let us. So we go to the site with a biologist. Carrizo National Monument has protected species. One of them is kangaroo rats. So these are ground squirrels, a version of it, and they are everywhere. It's impossible to not affect their habitats. So a biologist comes with us when we're desperate again. She actually was super helpful. You go multiple weeks in advance. She displaces and they're nocturnal. You can see them during the daytime. She pulls them out, displaces them to another habitable location. We have to put fencing to make sure that no other kangaroo rats enter. And we go in and out within about a month's time. So there are ways of making some of these things happen, but sometimes they're just, they go through their mission. If their mission is not opened, their mission statement does not say that we have we try to request a permit from a wildlife habitat just south of the Carrizo Monument. It was a condor preserve. They're probably there only a certain period of the year for hatching their eggs, etc. I can show you pictures of trenches that are open in golf courses. It's straight, no damage, in and out in about 10 days. They said our work would be too disruptive. I said, we can do it at any time you want us to do. We'll be in and out. We'll place our spoils piles on tarps. You won't see any of the effects. They said it wasn't along their mission line to let this type of a research to be conducted. And then we're stuck. That's why these types of presentations are important to get across some of our limitations of collecting this data. And hopefully you have some connections, or if not, somebody you know of have connections that can connect us with.
So thank you very much.
You're very welcome. Thank you.